In this video, we'll be using a laser rangefinder and a clinometer, and we'll be employing the preferred method for tree height measurement, which is the Sine method. This tree model represents a wide-spreading tree on sloping ground, but regardless of whether we're on sloping ground or flat ground, the Sine method is a very straightforward, simple, and accurate way of measuring tree height. In this particular example, we positioned our eye level above the base of the tree, and in a future video we'll go ahead and position our eye level below the base of the tree. There's a lot of different benefits associated with the Sine method. For example, we can actually test different potential tops, and there's less estimating what actually is the top of the tree like we would need to do with the tangent method. With the Sine method, we could go ahead and test different tops. We could test this one, maybe this one back here. In addition to that, we don't have to do the cross triangulation method like we did with the tangent method, because we'll be measuring a distance directly to the top. We don't have to worry about the point on the ground that's below the top of the tree, because we're going to be measuring directly to the top of the tree and then also measuring directly to the mid-slope of the base of the tree. And in this particular example, we're going to be using a manual clinometer, and we'll also be using a Class 2 laser. One thing I will mention on a Class 2 laser is these can be dangerous if pointed in the eye, so definitely take precaution with that. Class 2 lasers with the red beam is a very good way of measuring distances indoors, whereas Class 1 lasers will be more suitable for measuring outdoors. So in a future video, we'll go ahead and take a look at some of the different Class 2 lasers and some of the best ones that are suitable for measuring trees. So to start with, what we'll be doing is determining where the top of the tree is. And let's go ahead and start with a formula. So we are going to be taking the sine of our angle, we'll call our angle x, and we'll start with the angle to the top, and we'll be multiplying that by the hypotenuse of that triangle. So if we make a triangle to the top, this will be the hypotenuse, and then we're going to be finding that opposite side. And that opposite side of that triangle will be right here. Alright, so as I was mentioning before, we can scoot back, take a look, and see what are the potential tops. We can use our manual clinometer to get an angle, and then we can go ahead and use our laser and get a direct distance to that top, and then we would employ the formula, and then we would know the height above our eye level to that potential top. And we can do that with multiple tops. It even becomes faster with a hypsometer that has a built-in clinometer along with the laser rangefinder. In this particular case, instead of doing all those multiple measurements, we're going to go ahead and settle on this one, which is the top of the tree model. So what we're going to do to start with is we're going to back up far enough so that we can see the top of the tree, and we will go ahead and take a distance measurement. And I have the laser set so that the starting point of the measurement is at the back of the unit. And what we have here is our eye level wouldn't be directly on the ground. So in this downsized scale here, we have our eye level 2 inches above the ground. And I also have the laser set in inches. And so from this point, we have 24.3 inches to the top. We can go ahead and write that down. All right. And then also 2 inches above the ground, we have our angle to the top is 46.7 degrees. Okay. So let's go ahead and do the math on it. We'll enter 46.7, enter sine, that gives us the sine of that angle, multiply by 24.3, and that gives us 17.7 inches. And let's go ahead and look at the triangle that we've created. Okay. So we had our angle of 46.7 degrees. We had our direct laser measurement to the top, 24.3 inches, which again gave us this opposite side of 17.7 inches, the height of the tree above our eye level. And let's go ahead and keep track of our measurements. Call that the point above our eye level, 17.7 inches. All right. And now we basically need to do the same thing to the mid-slope of the tree. We are on a slope, so we won't measure to this point, which would be the closest point. We need to measure to the side. And actually what I've done is I've put a little marker down there right next to the mid-slope of the tree model. So let's go ahead and do our laser measurement. Okay, and we have 24 inches. And then next we need to do our angle measurement to the base. And you know, we do have a little bit of swivel here with our clinometer. In the field it's not so pronounced, but on this small scale we'll actually need to move our tripod down. So that way when we swivel our clinometer, we're still at 2 inches above ground level. Okay, so when we take our angle reading to the base, we have 16.2 degrees. All right, and again, let's take 16.2 sine times 24, and that gives us 6.7 inches. All right, so essentially all we have to do is we have to add the vertical distance above our eye level and the vertical distance below our eye level, and we arrive at a total tree height of 24.4 inches. And let's also look at the triangle that we created with our measurement to the base. So again, we start here, which is our eye level. We went all the way down to the mid-slope of the tree, and we took our angle reading, 16.2 degrees here, and then we measured the hypotenuse of the triangle as 24 inches, and that gave us that opposite side of 6.7 inches. In the future, we'll definitely take a look at more examples utilizing the sine method, and we'll especially be looking at the process of using a hypsometer, which has that built-in clinometer, and that actually makes the process even faster. So with the press of a button, we would know the vertical distance above eye level to the top, and with a second press of a button, we would know the vertical distance from our eye level to the base, and we would add those two numbers together and arrive at an accurate tree height.